Howdy, my name is Frederick Hess, and today I'm going to be talking about radar modeling, simulation, and data engineering. Now, before we get into all the technical details, let's go ahead and cover why there's a need for cognitive radars and digital engineering. So, modern environments are extremely difficult to parse. Whether it be from communication systems, intentional jamming, or even other radars, there's a lot of noise that's going to be in any signal you get back. As a result, it is incredibly difficult to identify actual targets and glean any useful information. Now, this can be solved by using fully adaptive radar, which modifies radar parameters in real time to try and combat some of these issues, but that isn't always enough. An adaptive radar system may be able to adapt, but only within parameters that have been explicitly defined. It cannot learn, and it cannot build on itself. A solution to this issue is the use of a cognitive system, wherein you use a machine learning algorithm that can improve itself over time and even learn from its own experiences in order to perform better in the future. Now, another problem is that training detection algorithms is expensive and time-consuming. Anytime that you want to make a change to a design, when you're iterating on it to improve it, you have to actually build that new change. So, for example, if you want to have a larger antenna, then you need to build that new antenna, you need to hook it up to the existing system, you have to recalibrate everything, then you have to run through all the tests all over again. That is expensive, that is time-consuming, and it can even be dangerous. But it is necessary for training machine learning algorithms. Or it used to be. See, there's a solution called digital engineering, where rather than doing all of this expensive and time-consuming real-world testing, you instead create highly accurate digital simulations and do your testing and verification that way. So let's talk about those cognitive systems I mentioned. Cognitive Fully Adaptive Radar, or COFAR for short, is essentially an improved version of the fully adaptive radar that is already in a lot of modern systems. It operates on the sense, learn, adapt paradigm. First, it senses. It collects information about the environment, usually things such as backscattering and clutter information. Then it will learn. It takes all of this gathered information and it learns environmental statistics with it using its cognitive systems. And then finally, it adapts. By using what it's learned, it will change the radar parameters in real time to optimize detection and estimation. Now, a big part of fully adaptive radar, and COFAR systems by extension, is clutter channel impulse response, CCIR, estimation. Clutter refers to unwanted reflections from the ground or sea that can obscure weak targets if not handled properly. However, it is extremely computationally expensive. But a solution to this is the use of Krylov subspace-based CCIR estimation. In traditional methods of CCIR estimation, the CCIR vector is found by using least squares math, but that involves inverting a large matrix, which is extremely computationally expensive and far too slow for a radar that needs to adapt every pulse. So the solution is a Krylov subspace-based CCIR estimation. It uses a conjugate gradient algorithm, and it essentially takes an initial guess and then checks the error and corrects it step by step in the best possible direction in order to find a good solution. And after just 30 iterations, it converges to a solution that is near identical to the least squares method while being significantly less expensive. As you can see in the graph here, the initial iterations are very far off, but, as I said, once it reaches the 30 iteration mark, or honestly even the 25 iteration mark, it is extremely close to the full least squares method while taking significantly less time to process. Now, it's time to talk about digital engineering. So digital engineering and AI testing is fantastic because it allows you to train detection algorithms and do iterative design without the expensive and time-consuming process of actually physically building and testing something. It involves 3 phases. The first phase is creating a digital twin. A digital twin is essentially a highly detailed simulation that represents both the system under test, or SUT, and its operating environment. You use this digital twin to train AI models without real-world tests, but it still falls within expected real-world data. Phase 2 is introducing anomalies. In this phase, you test the model's robustness. So you take the AI model that you developed in phase 1, and then you start introducing anomalies. irregular weather patterns, swarms of objects, things like that are abnormal but still fall within realistic conditions, and you essentially ensure that the AI model still performs adequately under those conditions. The third and final phase is the black swan phase. This is where you start introducing still physically possible, but highly unrealistic and highly unexpected conditions. Things like massive swarms of tiny drones, or weather patterns that could theoretically happen but have never happened before. And you do this by using generative AI to create all of these conditions. That way, you can even account for theoretical conditions that a person wouldn't think of. And the idea is that by doing this, you ensure that your AI model can respond to not just conditions that you've thought of, but theoretically any condition that is physically possible, regardless of whether or not it's been seen before. This diagram shows how generative AI can be used to create synthetic data during the digital engineering process, especially in the final black swan phase. It's built around something called a generative adversarial network, or GAN. It has two parts, a generator and a discriminator. The generator takes random noise and creates simulated radar images, for example, cluster patterns or target returns that could theoretically exist but were not part of the original data. The discriminator then looks at both real and generated images and tries to tell them apart. Over time, the generator gets better and better and better at creating realistic examples until the discriminator can no longer even distinguish them from real data. This process lets us automatically create large amounts of physically possible but synthetic radar data, including rare or extreme conditions that are too dangerous, expensive, or unlikely to test in the real world, which is what makes it so useful. Thank you very much for your time, and I hope that this was an informative video to help you learn about the need and benefits of cognitive systems and digital engineering for radar.